Hello grade 11s, welcome to our first video lesson. So how this is going to work is I'm going to explain some topics, we're going to go over some questions together. So at any point in time, if you have to pause the video, if you have to go back and you have to re-watch some things, then please make sure that you do so. Okay, these lessons are supposed to be interactive. So you are supposed to engage, you must take notes as I'm taking notes, and pause the video where I instruct you to pause the video because there might be some things that we'll go over, and then after that we can go from there. Okay, so our first lesson that we're going to start off today is a brand new topic which you should be able to remember from last year, which is electrical circuits. So the first thing we're going to discuss are the topics that we looked at last year. So the heading for today is circuits, revision for grade 10, and the date will be the 5th of May 2025. Okay, so if we have a look at, if you can recall, rather from our grade 10 knowledge, we discussed three main things when it came to electrical circuits. And the first thing that we looked at is electrical current, which looks at how electricity is flowing through a circuit via electrical charge. Then the second thing we looked at is potential difference, which was the energy that was needed in order for electrical charge to flow. And the last thing that we looked at is the resistance, which opposed that flow of electrical charge, causing some sort of energy to be transferred, whether it was a light bulb or any other type of resistor. So the first thing that we look at in our lesson today is electrical current. So if you can recall, when we discussed electrical current, right? Electricity comes from this idea of electrical charge. Now, when we think about charge, we consider that there are two types of charge. There is positive charges, which come from the nuclei of atoms, and we look at negative charges, which come from the electrons in an atom. So charge is something that is required in order for electricity to form. Now, when we think about these electrical charges, if you can recall when we were doing coulombs last year and static electricity, there are forms of charge that is referred to as static. Now, static means that the charge is not moving due to some sort of insulator, right, that doesn't allow for the movement of the charge, but rather the charge builds up. And then after some time, if it comes into contact with a pathway, it will flow in that pathway, and then it causes that static burst of charge, or that zap that you feel when you touch the insulator. So if with electrical charge now, in order for static electricity to differ from regular conventional electricity or current electricity, it is not just the charge, but rather it is the movement of charge. Now, the movement of charge will take place through the movement of electrons. Okay, so when electrons flow through a conductor, so we have these negatively charged particles, which will form the electrons, will move from one side of the conductor to the other side of the conductor. That generates what we refer to as current. So when they move, they're going to essentially release this electrical current that is going to flow in the opposite direction of the electrons. So that current is then generated by moving charges, which generates an electric field that will then convert the energy into electrical energy that will obviously then form the electrical current or the electricity that we find inside the circuit. So if we look at then what current is defined as the rate of flow of charge. Okay, so that is something that is also a SAGS definition that you'll find inside your SAGS document. So current is defined as the rate of flow of charge. Now we can derive an equation from this definition that we have. If you can recall, when we talk about rate, we talk about a change in time. Okay, because it's about the movement of charge. So that means that if charge moves faster inside the conductor, then we're going to have more current inside the conductor. So it's all about how fast these charges are moving. And if you can recall, that charge in a circuit is represented using the letter Q. Okay, you'll see that inside some definitions they use a small letter Q, which is also perfectly fine. Okay, so if current is the rate of flow of charge, then it must be the charge that is divided by that rate, that time, in order to get the rate. So we would have I for current is equal to Q divided by T, where I is for the current, which is measured in amps or amperes. You have Q, which is your charge, which is measured in coulombs. And you have the time, which is measured in seconds. So this is one of the first equations that we look at. It comes from the definition of current. Okay, so through the movement of current, the movement of charge rather, we have this current that is going to flow. But if we think about how this is going to happen, okay, it's all good and well to know that current is the flow of charge, but what is it that causes this charge to flow? Because something has to give it energy in order for it to move. So that's where we look at what is called potential difference. Okay, so potential difference is basically, when we looked at potential energy, we looked at how there is this difference in energy which is going to move, which is converted into that kinetic energy. So potential difference comes from this idea that we have potential electrical energy. And again, that comes from this idea of the movement of charge. So if we considered a conductor, so a conductor, if you can recall from chemistry, we said that, well, conductors allow for the flow of electricity because they are metals. So all metals are conductors, and the reason why is because they have these positive kernels and a sea of delocalized electrons. So the delocalized electrons means that those electrons are going to move. So if we think about a metal, we would have these positive kernels that would exist throughout the metal object. Okay, so those positive kernels come from the nuclei of all the atoms that we find. Okay, so those positive kernels are then technically the nuclei. Then the electrons are scattered throughout the metal, and they are able to move from one side to the other side, right? They are delocalized. So what happens is that we provide energy into the system by moving electrons closer to one side of the metal. And when we do that, we create this potential difference, right? Because if you think about it, these electrons want to repel one another and move towards the positive side. But we create this system where one side, where they are pushing apart. And so that causes a negative side of this piece of metal, and then a positive side of the metal would be on the side where there is less electrons. And by doing that, we create this apparatus which we refer to as a battery. So when this occurs, then we have this potential electrical energy. So the potential difference that we have is due to this work that we essentially create by separating these charges. Now, work is something that we discuss a bit later on, but essentially it boils down to the fact that we are looking at the energy. So if we consider then the potential difference, we can define it as the work done per unit positive charge. So that is also a SAGS definition. So it is the work done per unit positive charge. And the reason why we refer to it like this is because technically the electrons are negatively charged, which means that the current that flows in the opposite direction would basically be referred to as that unit positive charge. So when we try and look at the equation, we have a second equation that we can use where the potential difference is equal to the work done per unit charge. So per then would refer to division. So we would have the equation that looks like this, where we would have the V, which is the symbol for potential difference, which is measured in volts. We have the work, which is going to be measured in joules, because like I said, it boils down to the fact that there is this energy that we're going to have, and the charge, like before, which is measured in coulombs. So that gives us the second equation that we have in this section. Okay, so we understand that electrical current is used measuring the rate of flow of charge, and the potential difference measures the work done per unit on that positive charge. So essentially we understand that electrical current is the way, so it is rather how charge moves. So that is what electrical current is answering, is the question of how charge moves. And potential difference answers the question of why charges can move. Okay, so that is essentially those two fundamental topics. Now we look at resistance. So now resistance is going to look at the relationship between these concepts. So resistance now looks at, first of all, the fact that all charge is going to experience some sort of resistance. So resistance is understood as this opposition to the flow of charge. And it's important to remember that everything has some sort of resistance to charge. Okay, even conductors. So nothing is going to possess zero resistance. Okay, there is always going to be resistance that we have inside of a conductor. Okay, so the relationship between current and potential difference is what is found in resistance. And that makes sense, because if current refers to how charge is flowing and potential difference refers to the energy that is needed for charge to flow, then surely if there is resistance, then that is going to basically cause a decrease in the flow or an increase in the flow, which is going to then force the potential difference to then either increase the flow or decrease the flow. Although we wouldn't really look at decreasing the flow unless it was for something specific, in terms of a resistor that can't handle a high amount of current. Okay, so the reason why there is this resistance is because if we again consider a conductor, okay, a conductor is allowing for this movement of charge, but these charged particles are going to collide with one another. Okay, they don't move perfectly in these neat little rows. Okay, they are trying to move throughout this conductor from one side to the other side. So they bounce off the sides of the conductor, and they also bounce into one another. Okay, so due to these collisions of charged particles, we have resistance. Now, what happens is that as these particles collide and this resistance is going to form, then what happens is that the temperature of the conductor increases. As there are more collisions, which means more resistance. So there are factors that are going to affect the resistance of a particular conductor. Okay, and these are these factors you have to know off by heart. So there are 4 factors that are going to affect resistance. Okay, the first factor is of course the type of conductor. So if we have a better conductor, just based on the type of material, you will have less resistance. Okay, now the second part, or the second factor rather, is the length of the conductor. So if you think about the length of the conductor, consider 2 conductors. Like this. You can see that clearly the one conductor is a lot longer than the other conductor. Now if we think about how charge is moving, we almost imagine that charge is like these little men that are running from one side of the conductor to the other side of the conductor. And just like people, in order to move, you exert energy. Now if you consider points A and B, clearly there's going to be more energy needed for this man to go from A to B. There is less energy that is needed, right? Because the length is shorter. But if he's running from this side all the way to that side, you can see that there is more energy that is going to be needed. So if there's more energy needed, then the resistance is more. So the longer conductor will have more resistance. Then the third thing is the thickness of the conductor. So again, we think of, imagine having a conductor with that thickness and having a conductor with this thickness. Remember, we spoke about the fact that there is this collision which causes more resistance. So if there is less space for these particles or these men to move, then what's going to happen is they're going to collide more into one another and more into the conductor itself, which would mean that there is going to be an increase in the resistance. Whereas if there's more space to move, then it's easier for these particles or these charged men to go from one side to the other side. So that means that if you have a conductor that is going to be thicker in terms of the diameter, then you're going to have less resistance. Okay, so a larger diameter in a cable, for example. Okay, and then the last factor is of course the temperature. And like we said, if there's more temperature, there is more resistance, because resistance causes temperature to increase. So that means that the more the temperature, or the higher the temperature, then the more resistance. In the same way, you could consider 2 cables with those men running from the one side to the other side. And now we imagine a cable that is going to be a lot hotter. So obviously these men are going to be less inclined to want to run across the hot conductor, whereas the cooler conductor, it is much easier to run. So that's something, just a way for you to hopefully remember these a bit easier, because it is very important that you learn how these factors are affecting the resistance. Okay, so looking at the relationship now. So resistance is essentially this constant that looks at a ratio between the potential difference and the current that flows through it. So now that we understand what resistance is, we need to look at what that means for the other two concepts that we've already discussed. So resistance is the ratio between the potential difference, which is the energy needed to move the charge, and the current flowing through it. So basically that means that the resistance is this ratio between current and voltage. And if you can recall from maths that a ratio is just a fraction. So this gives us the third equation in this topic, which says, well, the resistance is equal to the voltage divided by the current. Where R is the resistance, which is measured in ohms. V is the potential difference, measured in volts. And the I is the current, which is measured in amps. So this relationship that occurs between the potential difference and the current is what we call Ohm's law. So Ohm's law, which is also a SAGS definition, you must be able to state the full Ohm's law, which says that the current through a conductor is directly proportional to the potential difference across the conductor at constant temperature. So it's very important that you are able to recite this word for word. Okay, we say that the current through the conductor, so not the current across the conductor. That doesn't make sense, you get it wrong. So it's the current that flows through a conductor, which is directly proportional to the potential difference across the conductor. Okay, and it's important that you get the order right. It's the current that is directly proportional to the potential difference. Okay, because we see it as this understanding of, well, you don't change the potential difference in a circuit, in the sense that if you have a battery, it's going to have a maximum potential difference. Okay, there's nothing that you can do to that battery to increase the potential difference unless you add another battery. So we say, okay, well, that means that the flow of charge must be related to how much energy we have to move that charge. So the more energy, the faster the charge is going to move. If we have less energy, then the charge is going to move slower. But this relationship is only true if the temperature remains constant. And temperature remaining constant is basically resistance. However, we don't use the word resistance in this equation, okay, and in this law, because the resistance is calculated via this ratio. So we specifically mean that the temperature is remaining constant. Okay, and you cannot exclude that from the definition, because the moment that it is no longer constant, then the law is no longer going to be obeyed. Okay, so this is very important. So let's look at, in your textbooks, on page 91, exercise 23. I will do the first few questions with you. So it says, study the following diagram and answer the questions to follow. Okay, you're given the following circuit diagram. Okay, so it says calculate the equivalent resistance of the circuit. So that's something also I should have actually mentioned for the resistance, on calculating the resistance. So let me add a page first and then we can go over it. Is that when we are calculating resistance, right, there are two types of circuits when we're calculating resistance. Okay, the first that we look at is a series circuit, and we look at a parallel circuit. So this is just basically how resistors are arranged. So in a series circuit, the resistors are arranged in such a way that there is only one pathway for the current to flow. So that is what a series circuit is. It means that there is only one path for current to flow. So current has to flow through every single one of these resistors, but there is only one way to do it. There is no split or no variance in the way that the current can flow. Okay, so that is then what we refer to as a series circuit. So when we calculate resistance, we say, well, the total resistance is just the sum of all the resistors that we have. So in order for us to understand then how this works, if current is going to flow in one direction, then it must be the same throughout. So another important note here is that current remains the same in a series circuit. So that means that the total current is equal to the current at one point, which is equal to the current at another point, and so it keeps continuing. So if you take an ammeter, which measures current, and you put it here, it will be the same as the current here, and the same as the current here, and so that doesn't change. So the total current is equal everywhere. But now, when we look at potential difference, so resistors in series are considered to be potential dividers. So that means that the potential difference in this part will be different to the potential difference in that part. And so it's going to be different. It changes. And that is because the resistors are going to use some of that energy for the circuit to flow, for the current to flow. So that means that the V total of the whole circuit is equal to the sum of all the voltmeters. Now if we look at a parallel circuit, do I have enough space? Let me just double check. Let me do this at the bottom. And I'll move these to the side. So now when it comes to a parallel circuit is when there is multiple paths for the current to flow. So pathways for current to flow. So if this is true now, then we look at, again, just like we did before with calculating the resistance, the current, and the voltage, we need to then realize, okay, well, if there is multiple pathways, now instead of just one pathway, so we know that because there is a break in the connection where current can flow in multiple different ways. So it will start at this point and end at that point. That is where the multiple pathways start. So calculating the total resistance in a parallel circuit is going to be equal to 1 divided by R1 plus 1 over R2 plus 1 over R3, and so you just keep adding the resistors in parallel, and then when you have that total, you'll take it and you'll put it to the negative 1. Okay, that is how we calculate the resistance in a parallel circuit. Then, if I'm going to consider now the current and the voltage. Now, because current has multiple pathways to flow, then current, so the resistors in parallel are considered current dividers. Meaning that if I want to calculate the total current in a parallel circuit, then I will have to add the current that splits. So that means that the current that flows through here is going to be different to the current that flows through there, and different to the current that flows through here. Okay, so that's very important to take note of here, is that then the total current from this part to this part is equal to the sum of the 3 currents. But now if I look at the potential difference, the potential difference is the same. So that's because the potential difference from this point here to that point there is equal. Okay, it doesn't change. So that means that the potential difference at this point and the potential difference at this point and at that point are all equal. So the V total is equal to V1, which is equal to V2, which is equal to V3, and so on. Okay, so let's use then these principles in order to calculate the basic questions in exercise 23 now. So it says calculate the equivalent resistance of the circuit. So let's now identify. Firstly, I have two resistors, here and here. I notice that both of those resistors are in parallel to one another. So if they want to know what the effective resistance is, I say, okay, well, if there's two resistors, then I know that the R total for the parallel component is equal to 1 over R1 plus 1 over R2 to the power of negative 1. So that will be 1 over 2 plus 1 over 4 to the negative 1. And if you put that whole thing in your calculator, you'll get 1.33 ohms. Okay, don't forget the unit. Okay, it's resistance, which means that it's measured in ohms. Okay, then the next one says, what will the reading on the voltmeters be if the potential difference across the cell is 12 volts? So if the potential difference across the cell is 12 volts, and that's basically telling you that the V total is 12 volts. But now if you can recall from what we discussed in parallel circuits, we said that the potential difference remains the same. So that means that this V here and this V here will have the same reading, which will be the same as the total voltage, which is going to be 12 volts. Then it says calculate the total current of the circuit. Use two methods. Okay, so calculating the total current, we can use the first method, which is going to be using Ohm's law. So Ohm's law says that resistance is equal to V over I, which would mean that to calculate current, we would say, well then, current is equal to V over R. Okay, if we continue, we'll see, okay, well, if they want current total, then I total is equal to V total over R total. Now we know the V total is 12. The R total we found in question 1.1, which is 1.33. So the final answer here is going to be 9 amps. Okay, so that is the way that we would calculate that particular current. Now if I look at the second type of the second method, I can also use the ratios. So the ratios, specifically, I can say, well, if I look at the ratio here, I can see that it's going to be, I can add the ratios for these branches here. Because I know, okay, well, this value here is going to be equal to 12 volts, and this potential difference here is also 12 volts. So I can calculate the current through this specific part of the circuit, and I can calculate the current through that particular part of the circuit and add them together. So the current that flows through the 2 ohm resistor, still using Ohm's law, is equal to V over I, which will be 12 volts, V over R, sorry, which will equal to the 12 volts divided by that resistance, which is 2. And I get a total of 6 ohms. 6 amps, sorry. So if I know that 6 amps flows through the 2 ohm resistor, then I calculate the current that's flowing through the 4 ohm resistor. So again, I can use 12 volts divided by the resistance, which is going to be equal to 4. So 12 divided by 4 is 3 amps. Now if I wanted the I total, I would say, well, that's the same as I1 plus I2, which is equal to 6 amps plus 3 amps, which is 9 amps. So these are the two methods that I can use. I can say 9 amps by calculating the current individually, or I can just say, well, R total is equal to V total over R total. You can use both methods. Okay, in this particular question, they asked you to use 2 different methods just to sort of expose you to a way that you can calculate it. Okay, so for your homework, I would like you to complete number 2 and also number 3. So then we'll go over the corrections for the next time, and then just make sure that if you need to go over anything in this lesson that you do so, and then I will see you on the next one.